Okay, so we're going to talk about tangent and cotangent functions today. So on the screen right now, you see a snip from a homework assignment that you guys did where you graphed each of the parent functions and plotted all of the unit circle values. I really liked this graph, so I just stole it from someone's paper. And so we see that we have the asymptotes that are labeled, and all of the asymptotes happen at odd pi over 2s. So one way that you can write that is what we have here, is we have that the asymptotes are pi over 2 plus n pi, where n is an element of z. And I would just add in there an x equals because they are vertical lines. And so we'll just throw in an x equals pi over 2 plus n pi, where n is an element of z. Of course, you can combine those two terms together if you would like and put it as one fraction. That's totally fine as well. All right. And then we have our zeros. Our zeros happen here at negative 2 pi, and they happen at negative pi, 0, pi, 2 pi. So those are all multiples of pi. So all of the zeros are going to be at n pi, where n is an element of z. Perfect. And if this is an even or odd function, we can see that it has origin symmetry, so it will be an odd function. And then we have our domain, we have our period, and we have our range. So our domain is everything except for the asymptotes. So x such that x does not equal. And then here we have that written instead of as two separate fractions, but 2n plus 1 quantity times pi all over 2. Of course, n is an element of z. Don't forget that piece. If you forget n is an element of z, then you will not get full credit. The range is infinite, so negative infinity to infinity. And the period here we can see is just pi. So one period exists between two asymptotes that are consecutive. So that represents one period. This second piece here, one period. Over here, one period. So inside each blue box is one period. So this is different than than sine and cosine, because sine and cosine have a period of 2 pi, whereas tangent has a period of 1 pi. All right, so let me just show you a graph that is not so good. Here's one that is not so good. Oh, where are all the points? I don't see the points that I should see on there, right? And it's just a yucky, ugly squiggles. It's not accurate. No bueno. So make sure your graph does not look like something like that. Rather, it looks like this. Beautiful. Asymptotes drawn, asymptotes labeled, points plotted. Okay, so let's take a look at a graph so we can learn how to graph transformations of tangent functions. And let's start with this example here. So here we have this function, y equals 2 tangent of x minus pi over 4 plus 3. So we can start by finding out the information that's critical to the graph. So as we've done before, we've done period, amplitude, phase shift, and vertical shift. So period in this case, since the parent function period is pi, then that means that the formula for the period here for tangent functions is absolute value of just pi divided by b, because the numerator is simply the parent functions period, and then you break it up based on what those horizontal stretch or shrink is going to be. Okay, so we have absolute value of pi over b. So in this case here, absolute value of pi over b, our b value period in this case is still pi. Now the amplitude, very, very important here. I wrote that down, but I wanted to write it down to tell you that it does not exist for tangent functions. We have an a value, and the a value tells us whether it's going to reflect. Okay, so I'm just going to put down here that a is equal to 2, so that means that there is no reflection. Okay, so I can keep that in mind. And the a value is going to be 2. It will be represented on the graph, but it is not called amplitude. All right, we do have a phase shift. The phase shift is in the same location. And so we have a phase shift of pi over 4. And we're going to give a direction, so it's pi over 4 right. Also, we have a vertical shift of 3 and also give a direction, so that is 3 up. Now, you can find different strategies for graphing tangent functions and cotangent functions. Because they have asymptotes, and we know that one period is contained between those two asymptotes, I like to graph the asymptotes and then use symmetry to find in between. Because if I go back up to my parent function real quick, I can see the symmetry that I have here. So I can see that here's an asymptote, here's an asymptote. This kind of turning point, that point of inflection is its formal name, is halfway between the asymptotes. And then halfway between the halves, so halfway between this half here, I have this point, which is at 1. And halfway between the half on the left side here, I have this point here, which is at -1. And so I still have like the half, the first half, the second half. So it's still divided up. The period is divided into 4 kind of equal parts to find the significant critical values that I'm going to require you guys to graph. Okay. All right. We know that this critical value here is at -pi/4 -1, and the green one is at pi/4, 1, just by knowing what we know about the tangent and the unit circle. Okay, so using that concept, let's go back to our graph. So I'm going to find asymptotes. So on the tangent function, I have asymptotes at pi/2, -pi/2, and so on. So I can choose one of those asymptotes, and then I can use that to find my transformed asymptote, and then the period to find the next one, and so on. So I will find what I'm going to call, instead of the first point, I'm going to find a first asymptote. So you can use x equals pi/2. Sometimes you might want to use x equals -pi/2. Here we are shifting to the right, so maybe you want to use -pi/2. It doesn't really matter. I will use x equals pi/2. So I'm going to take that asymptote, x equals pi/2. Because it's an x value, it's going to transform based on the horizontal transformations. So my horizontal transformations are my b value and my c value. So I can see here that my b value is just going to be 1. My c value is going to be pi/4 to the right. So what I'm going to do is I'm going to multiply by a 1, and then I'm just going to move to the right by pi/4. So I'm going to add pi/4. And so that's going to give me my first asymptote then. If I do pi/2 plus pi/4, that's going to give me x equals 3 pi/4. Now I'm going to hang on to that one. I know that my period is pi, so the distance between the asymptotes is the period, right? So I'm going to have one asymptote. Just going to make a quick little sketch here. X equals 3 pi/4. My next asymptote to the right or to the left is going to be a distance of the period. And my period in this case is pi. So that means my next asymptote here is going to be at x equals 7 pi/4. Cool. If I were to go backwards, my previous asymptote would be pi before that, so x equals -pi/4. Okay. And I forgot to put this in the directions, but let's graph 2 periods. Okay, so I'll use that from -pi/4 to 7 pi/4. Okay. All right, and then let's think about our vertical shift. So our vertical shift is going to be representing kind of our middle, right, our midline. So I need to have a vertical shift of 3 units up. So I'm going to make sure that I draw my axes so I can represent that. And then my A value represents my kind of double half points. So let me go ahead and start getting this graph put together for us. So let's draw, I'm going to have to get to -pi/4 here. So I'll need to start right here. And I'm going to be going up 3 and my A value is 2. So I'll talk more about that, but I'll just put this right here. Okay, so I have a first asymptote point. My asymptote here is going to be, let me change this to a yellow. All right, so yellow for my asymptote. So I have a first asymptote at 3 pi/4. I have to figure out what I have to count by. I forgot to do that. So figuring out what to count by on your x's, we're going to use the same concept that we did in our sine and cosine functions. We can take the period divided by 4 because we still have those divisions of symmetry. So the period divided by 4, so that's pi/4. The other thing we looked at was the phase shift, which is also, in this case, pi/4. So we put that together. That tells us to count by pi over 4s. All right, so let's mark that on our graph. So here I have pi over 4, and on my y-axis, I'm just going to count just to make this a little bit bigger for you guys. I'm going to count, I'm going to count by ones, just ones. Because I'm not sure if I'll fit it otherwise. All right, perfect. So now I can start to put in my asymptote. So my first asymptote here is at x equals 3 pi over 4. So 1, 2, 3 pi over 4. It's going to be right here. You can use a highlighter for asymptotes, or you can use dashed lines. Doesn't matter. I have another asymptote at negative pi over 4. So I can draw that one in here. X equals negative pi over 4. And then I have another one at 7 pi over 4. So here is my third one. And I asked you to graph 2 periods. And so we're going to have 2 periods here. And that's all I need. So you need those 3 asymptotes, and I can label those asymptotes. Always label your asymptotes. So I have x equals 3 pi over 4, x equals 7 pi over 4, x equals negative pi over 4. Now, the midline, the vertical shift, is always going to represent where that middle point is. So now halfway between the asymptotes, I'm going to have my middle point. Okay, so I know that my middle point is going to be on this midline of 3 units. So if I go up 3, I'm just going to put in a little dashed here, and that's representing my midline. So halfway between, I'm going to have my center point. So I can just go ahead and put that center point right here. So here I know I have pi over 4 comma 3, and here I know I have 5 pi over 4 comma 3 for that midline. All right, continuing on, then I'm going to go half of the half. So half of each of the halves, and then my a value. So my a value tells you how far above or below the inflection point you're going to be. So if I go up from the inflection point 2 units, my a value is 2. So for my inflection point, I'm going to go up 2 units, and then I'm going to go halfway between. So up 2 units, and then I'm going to go halfway between. And I have this point right here. So I know that that's going to be my point. Remember I said there's no reflection, so I know it has the same shape as my original parent function. So it did not flip at all. And then I'm going to go in the other direction. I'm going to go down 2, and then I'm going to go over between, and it's going to be right there. So those are going to be my other 2 points that I'm going to graph. So going ahead and plotting those 2 points, I have this point right here, which I know then is pi over 2 comma 5, and this point down here, which is at 0 comma 1. Now, when I connect my points, do make sure that you connect them with a nice curve, goes through, turns, and then comes up. Make sure there's no double bubbles in your tangent function. So I'll do the second period here. I have this point, and I have this point. And again, you only need to label one period worth of points, and there we go. So sometimes when I say no double bubble, sometimes I see students do this. They go up like this, and then they turn this way, and then they go turn this way, and then they turn this way again. There's no double bubble. Shouldn't be anything like that. Okay? And there we have our tangent function. So there's an example of how you can graph your tangent function. All right, so I'm going to end this video here, and I will have another video for you for the cotangent function.